In today's class, we will look at what is called a Ferrous diagram. Now we have seen partition. So when you take a partition of a positive integer n, so we are representing n in the form n1 plus n2 plus etc. nk. So this is a partition, k parts, and the parts are of size n1, n2, etc. nk. So here n1, n2, etc. nk, they are going to be positive integers. When number represent we write in the form n1 greater than or equal to n2 greater than or equal to n3 greater than or equal to nk. Now the Ferrous diagram is a diagram which is used to study the partition. അല്ലെങ്കിൽ പാർട്ടീഷനെ റെപ്രസെന്റ് ചെയ്യുന്ന ഒരു ഡയഗ്രാമാണ് ഈ Ferrous diagram എന്ന് പറയുന്നത്. So let us look at what is the definition of Ferrous diagram and how to draw the Ferrous diagram for a given partition. So a convenient tool in the form of a diagram to study partitions of integers is called Ferrous diagram. And let's look at how do we get the Ferrous diagram. So the Ferrous diagram for a partition n equal to n1 plus n2 plus etc. nk of positive integer n is an array of asterisks in left justified rows with ni asterisks in the ith row. And for a partition P, f of P denotes the, so this is a notation for the Ferrous diagram. So it denotes the Ferrous diagram for P. Now suppose you are given the partition, say you are given a partition for the number 15. So the partition is 6 plus 3 plus 3 plus 2 plus 1. So you have the partition f of P denoted by, so you will have asterisks in the rows. So corresponding to 6, you will have 6 asterisks. So there is an array of asterisks in the justified rows with ni asterisks in the ith row. So the ith row will contain ni asterisks. So first row will contain n1, second row will contain n2, and the kth row will contain nk asterisks. So corresponding to 3, you will have 3 asterisks. Then again for the next one 3, then the next one you will have 2, and for the last one you will have 1. So this is how we write the Ferrous diagram for a given partition. ഇനി നമുക്ക് ഇതിന്റെ transpose എടുക്കാം. That means you can interchange the rows by columns. Now when you interchange the rows by columns, that will again give us a partition for the given positive integer. So the transpose of Farrow's diagram, where the rows are replaced by columns, is again a partition of the same number. കാരണം ഇവിടെ total number of asterisks will remain the same even if you interchange the rows and columns. So the transpose, so we denote the transpose by ft. So the transpose ft of the Farrow's diagram is the Farrow's diagram whose rows are columns of the Farrow's diagram of F. So let us look at the Farrow's diagram for this example. So F transpose of P will be given by, so ആദ്യത്തേതില് 5 asterisks വരും in the first row, and the second row you will have 4 and then 3, then you have 1, 1, 1. So here you can write 15 as 5 plus 4 plus 3 plus 1, 1, 1. So that will be required. That is the Farrow's diagram which gives the transpose. Now these two Farrow's diagram, they are called as the conjugate partition. So if one is a transpose of the other, so then in that case the partitions are said to be conjugate partitions. So here this is the conjugate partition of this one, 6 plus 3 plus 3 is 2 plus 1. So two partitions of n whose Farrow's diagrams are transpose of one another are called conjugate partitions. So therefore here, so let me call this as so this is a partition P, and here you have Q equal to 5 plus 4 plus 3 plus 1 plus 1 plus 1. So here P and Q are conjugate partitions. We have Q and P നമുക്ക് 6 plus 3 plus 3 plus 2 plus 1 ആയിരുന്നു നമുക്ക് P യുടെ വാല്യൂ വന്നത്. Now you can see that when you have conjugate partitions, so the number of parts in P will be equal to the largest size in Q. അപ്പം QP-യിൽ നമുക്ക് 5 parts ഉണ്ട്. So 5 parts ഉണ്ട്. So the number of parts in Q, the P will be equal to the largest size, that is 5 in Q. Similarly, here the number of parts are 6, that is equal to the largest size in P. So that is an observation we obtain from the conjugate partitions. So let us look at how do we prove that. Okay. So let us a theorem. So let k comma n belongs to set of all natural numbers with k. So k must be less than or equal to n. Then only we can form a partition. So here n will be a positive integer and k is also a positive integer, and we are going to form a partition with of n with k parts. So then number of partitions of n into k parts is equal to the number of partitions of n into parts, the largest size of which is k. So the number of partition of n into k parts will be equal to the number of partitions of n into parts where the largest size is equal to k. So here how we prove this result is we will form a bijection between the conjugate partitions. So for that we will use the Ferrous diagram. The Ferrous diagram will bijection establish you. So that will give the proof for this result. So let us look at the proof for this. So let P be the family of all partitions of n into k parts, and Q be the conjugate partition. So Q be the family of all partitions of n with largest size k, and now let us define a mapping from P to Q. If we can show that it's a bijection, then cardinality of P will be equal to cardinality of Q. So that will be the required result. So let us define a mapping F from P to Q as follows. So for each P belongs to P, we put F of P to the partition of. So here the Ferrous diagram of this partition is mapped to the corresponding conjugate partition. F of P transpose map. So we put F of P to be the partition n. This Ferrous diagram is F of P transpose. So therefore we can obtain a bijection for partition of n into k parts എടുത്തു കഴിഞ്ഞാൽ അതിന് corresponding ആയിട്ട് നമ്മൾ transpose എടുക്കുമ്പോൾ the largest size will be k. So therefore F forms a bijection between P and Q. So that implies cardinality of P is equal to cardinality of Q by bijection principle. So hence you get the